In this video, I will show how we can import and process a gel image file in Bionumerics. As you can see, I am working on a brand new blank database. In that case, before I can start importing gels, I will have to create a fingerprint experiment type. In the Experiment Types panel, I press the button Create New Experiment Type. A menu pops up from which I select Fingerprint Type. On the first page of the wizard, I enter a name for the fingerprint type. I press Next, and here I can specify what type of gel fingerprint data I will be using. I enter 2-dimensional TIFF files and 8-bit OD depth and press Next. On this page, I can specify whether my gels are scanned as white bands on a black background. Since the images are captured with ethidium bromide under UV light, I answer yes to that question. I can also change the background and foreground color, but I leave these settings like they are and I press Next. On the last page, I can apply a default background subtraction to the densitometric curves. However, I can change most settings afterwards as well, so for now I leave this setting disabled and I press Finish. The new fingerprint type now appears in the Experiments panel. To import the gel in the database, I press the Import button. Under Fingerprint Type Data, I select the option Import Gel File, and I press Import. Next, I browse for the location of the image file. Optionally, I can open the gel in an image editor before I import it. This is useful if you want to import other image types than grayscale TIFF, such as JPEG, GIF, or True Color TIFF. It can also be useful if you need to rotate or trim the image. Since there is no need to edit this gel image before importing it, I uncheck this option and I press OK. The new gel appears now in the Files list. It is marked with a red N, meaning that it is not yet processed. The gel file can be opened simply by double-clicking on it. This is the fingerprint file window, which is initially empty because I haven't defined any lanes on the gel yet. We first need to process the gel by pressing the button Edit Fingerprint Data. The software asks me which fingerprint type the gel belongs to. Currently, only a single fingerprint type is defined, so therefore I just press OK in this dialog. The gel processing flow consists of 4 separate steps, and for each of these steps there is a dedicated panel present. The panel strips to define the lanes on the image, the panel curves to calculate the densitometric curves for the lanes, the panel normalization to correct distortions on the gel so that it matches the reference system defined for the fingerprint type, and the panel bands to search for bands on the lanes. You can go back and forth between the different steps by clicking on the corresponding tabs. The same can be achieved by pressing the arrow buttons. With the zoom slider on the left, I can zoom in and out of the gel image. In the first step, the lanes on the gel need to be defined. With the green rectangle, we can indicate that part of the gel that contains the actual profiles. If needed, I can use the Shift key to distort the rectangle locally. I can have the software search the lanes automatically by pressing the Auto Search Lanes. I enter an estimated number of lanes. In this case, there were about 20 loading slots. If needed, lane positions can be modified individually. They can also be bent by holding down the Shift key and dragging one of the nodes. If required, I can change a number of parameters in the Settings dialog box. I can define the thickness of the gel strip, which is now 31 points. I will change this into 60 to cover the full width of the lanes. The number of bending nodes on the strips can be changed as well. Optionally, I can perform a two-dimensional background subtraction on the image and remove spots and spikes. I press OK to adjust the gel strip thickness. Now I can proceed to the Curves tab. Here, the areas of the lanes on which densitometric curves are calculated are defined. The areas that will be used are indicated between blue lines. The densitometric curve for the active lane is shown in the right-hand panel. For this step again, I can change a number of parameters in the Settings dialog box. The thickness of the averaging area, for example, which is now 7 pixels. I will change this into 15 to have a smoother averaging. As an option, I can define more nodes to allow bending of the splines. Background subtraction is a very important option. As you can see, there is quite some background on the present gel. Removing this makes the band searching and analysis functions a lot more reliable. I will allow background subtraction and I enter 10% as a disk size. I can also specify an averaging filter, including simple averaging and median averaging. And I can also apply a smoothing filter to remove noise from the curves. For PFGE patterns, the default value of 1% can be tried to start with. Richardson-Lucy deconvolution is a filter that accentuates individual peaks in composite bands, such as double bands or shoulders. I press OK to change the settings. Note that you can see the result of the changes in the right-hand panel, where the original curve is shown as a black line and the corrected curve is shown in gray shading. I press the arrow button to go to the normalization step. Normalization is an important process since it will make any new profile comparable with profiles that are already in the database. To do so, we will include reference markers that contain bands with well-defined molecular weights. These bands will become reference positions in our fingerprint type. By linking the marker bands to these fixed reference positions, the software can correct the gel in such a way that bands with the same size occur at exact the same position on all gels throughout the database. Since this is a new database, I will first have to define the reference positions that will be stored with my fingerprint type. I do this by right-clicking on a reference band and choosing Add External Reference Position. Now I enter the molecular weight of this band. Now the reference positions are defined. Obviously, if you know the sizes of all bands, it is better to enter them all to achieve greater accuracy. I still need to tell the software which lanes contain the reference markers. In this case, the reference markers are in lane 1, 7, 13 and 19. Next, I press Auto Assign. With the first option, the software automatically searches for the bands in the reference markers and links them to reference positions on the left. Updating the normalized view will straighten the image. With the distortion bars, the extent of the local distortion can be indicated using colors. I press the arrow button once more to go to the band step. This final step of the processing deals with the definition of bands on the gel. Again, there is an automatic search tool available to facilitate this task. A number of settings allows you to fine-tune the band detection based on the nature of the fingerprint type. For the current gel, the default settings will work fine. If needed, band assignments can still be modified manually. For example, I can remove individual bands. And using the Shift key, I can remove groups of bands. At any position, I can insert a band using the Enter key. This concludes the processing, so we can save the gel file and close the window. When we return to the fingerprint file window, we now see that 19 lanes have been defined. However, they are not linked to entries in the database yet. Linking lanes to entries can be done lane by lane or in bulk. For this example, I will add all lanes from the gel to the database. With the menu item Database, add all lanes to database. "19 entries are now automatically added to the database. As you can see, they all have a colored dot under experiment 1, meaning that they have a pattern for experiment PFGE SMA1. These entries can be annotated with additional information and used to create dendrograms from. Both topics are discussed in other videos.